Okay, this question we have also seen in class. So we said that already what is given to us in this is the state table, right? So state table means whatever the input is and what is the next state, right? So basically you present, so this is what is our state table, which tells us that, okay, how the next state is decided by the external and the QN, which is the present state, right? And based on that, what we did is we filled in the flip-flop inputs. Now, so what is the input is, because we know that we have to use in this SR flip-flop, right? So that is the flip-flop we are using. For this, if one needs to write truth table, you know, all of you, Q would be, so if they are both 0, 0, we know that it would Qn plus 1 will take whatever Qn was there. If set is 0, reset is 1, we know the output is 0, right? If set is 1, reset is 0, then we know that the output is 1, and irrespective of past state. And then if it is both 1, that is the invalid case, right? Which we have seen in the latch also. So that is the truth table of this. But now we have to build this state table using this flop. And that is when we said that the same thing what we have here can be converted. So this is your truth table. If we want to write in terms of S and R, which is what we have to find, then we have to convert this to something called excitation table, right? So excitation table means that you are looking at, okay, if I have to go from this state to, let's just fill this table, right? If I go to from 0 to 0, right? What are the possible inputs which are there at S, which is making this transition? That is what you are looking at, right? That is what your excitation table. So what we see is if 0 to 0 you are going, there are either case where you are S and R both are 0, 0, or is the case where you have the S and R is equal to 1. So that means S is definitely 0. That is what we can see. Because if S was 1, then Q would be 1. But R could be, because the initial and final state are same, that could be 1 or 0. Same way, you can now look at the second case where Qn is becoming 1, so which is 0 present state, next state becomes 1. How does it become 1? Obviously, this is a set transition which is happening, and set transition we clearly see that you have an input which is like this, right? This is the set transition. The same thing, if we look at this is the reset transition where the opposite thing we looks at. And then when we want to go from 1 to 1 is again a case where there's no change happening. So this is either 0, 0, or this is a case of 1, 0, right? So where the S becomes X and R is 0. So that is the first part where we have built now the excitation table, right? So this is how we can build here also. So I think these are just little bit changed, little bit in a sense that 1, 0 is before. So S and R we know it's a 0 and X, right? And 1 to 0 is this transition, which is 0, 1, right? And then there is a 0, 1. 0, 1 means 1, 0, right? We are just focusing on this part, right? And then 1 to 1 we see X0. So now based on that, one can now build the expression that, okay, what is the S and R? Because now we have to use this S and R to make this state table, right? That was our goal. And this state table is actually of a D flip-flop, right? That is what is the table. So now one would do is create this Carnot map. Carnot map means we have the table. So the Carnot map would be, uh, let's say first create the S. So now we create in terms of, or let me do it here on the top because the table I have filled there. So these are the two inputs, right, for the Carnot map. Inputs, let me just, yeah. So these are the two inputs for K map, right? Because based on this, and these are the two outputs. Oops. Okay. So then we are building, let's say S first. S, there are two inputs. That means either we can take like this, D and Qn, right? This is for S. For S, we see, so let's say 0, 1, 0, 1, right? So 0, 0, we see when it is 0, 0, it is S is 0, right? So 0 would not come. 0, 1 is also 0, right? So that is also done. Then we go to 1 and X, right? So this is what would come out of this, which you can clearly see that this is the case where S is basically D, right? Similarly, we can do the same exercise for the other input, which is R, D, and Qn. This is R, so this is 0, 1, 0, 1. And then you see where is R? R is 1, 0, 0. So this is a X part, and this is a 0, 1 part. So this is the 1 part, right? So when this is there, we can then again see there's a pair. Pair means the R is basically, which is D, right? So then one can see now if you want to make a resultant circuit, you can easily made in the same thing. So only thing you have to do is, let's say external, you have D coming in. D would directly go to S. There is no problem because S is equal to D, but R, you would have an inverter connected to it, right? That is the, and clock is anyway clock. So that is how you see that you, with the simple inverter and connecting it this way, you converted a SR flip-flop to a D flip-flop, which is what the state table initially was given, right? So that is what you see in this kind of problems is first, if you are starting from a state table, then the second step would be to generate the excitation table, looking at what are the input flip-flops which you are making with, or what is the your building block, right, of the circuit. So if it is, in this case, it is SR flip-flop. So then you see, okay, we use the excitation table for the SR flip-flop, and we calculated the SR flip-flop inputs in terms of the inputs of the state table, which were D and Qn, right? So that is how, and then we just represented, minimized the expression and then represented in the logic diagram. So that is the process for doing this kind of problems. Okay, we'll do more problems so that you can get a very, very good idea how to do this at different levels.